Got a few emails about questions on the homework, and just wanted to do a quick 1-minute recap here of confidence intervals. So on the homework, I think the problems that we're talking about doing a confidence interval for proportions were probably a little more obvious. You need to pull a little less information out of the problem to be able to do it. So I think you guys are probably feeling okay with that. But for when you're doing a confidence interval for the population mean, so for the true, average, whatever, sort of your strategy here is first question to ask: am I told the population is normal? And if you are, or if you're looking at a histogram and it looks approximately normal or something like that, then you have to ask one more question. So am I told the population standard deviation? So the true, this would be the true standard deviation, sigma. Again, in the sort of strange case that you are told that, then you can use the Z formula. If you don't know sigma, so if you're told a sample standard deviation or something about the so you're told a standard deviation about the sample, so it's involving the data that you collected, that's your sample standard deviation, and you want to use the t distribution. If you're not told anything about the population, so if you're not told that it's normal and you don't have the data to be able to look at it or anything like that, then you just want to make sure that your sample size is big enough. So if your sample size is bigger than 30, then the central limit theorem kicks in, and the t distribution is fine to use as well. So in that case, you'll also maybe it's sort of implicit here, but you're going to use the sample standard deviation S there. That's what's in that formula. So again, your strategy for a confidence interval, when you're talking about a population mean, do I know what the distribution is? Do I know that it's normal? And then if you don't know that it's normal, you just want to make sure that your sample size is at least 30. So hopefully that's the strategy that you took for your homework. Questions on confidence interval stuff? Did that homework assignment go pretty well? I mean, okay, I think it's a little more getting into some territory that's a little more straightforward than previously. Okay, well, we're going to resume our discussion with Chapter 8 today. I think we're going to pick up on page 5 of your notes here, section 8.2 and 8.4. And we're finally ready to sort of give sort of a general framework for how to do these hypothesis tests. So we've talked a lot about hypothesis confidence intervals already, and now we're talking about testing, which is related but has slightly different sort of framework of coming at the problem. And yes, and now we're ready to sort of talk about some general cases. So we have these 4 situations to consider, which are sort of exactly the same situation as we looked at in the confidence interval. So I'm going to move through these a little bit more quickly because I think this is something that's already familiar. So these 3 cases here, this is we're doing a test for a population mean, which would be mu, and then down here we're doing a test for a population proportion or percentage. And again, these first 3 situations, that's exactly what I just said for the confidence intervals, right? So first of all, we know that the distribution is normal with no invariance, sigma squared. Then we have a normal distribution where sigma squared is unknown. And then that third one, we don't know what the distribution is, and we don't know what the variance of the individual observations are. So again, this framework should feel very, very similar to what we've just talked about in Chapter 7. And yeah, I'm going to move through this a little more quickly. But anyway, the general setup is the same as it always is. We're assuming that we have a random sample, x1, x2, up to xn. So we have n independent observations that all come from the same distribution. And then we want to use those to construct a hypothesis test. Okay, so let's look at this first situation, that case where we're looking at a normal distribution where the variance is known. Yeah, thanks for the email. Okay, so kind of remember we have these sort of general steps to go through to kind of formulate what our strategy is here for these hypothesis tests. So our parameter of interest here, we're going to look at again mu, which is the population mean. And then the next step is we have to determine what our hypotheses are. So we have to figure out what the null hypothesis is and figure out what the alternative hypothesis is. So the null hypothesis for this class, it'll always be that mu is equal to something. So this is always the null hypothesis. Your null hypothesis is always that the population mean is equal to some value. So this is a hypothesized value. And then your alternative hypothesis will be one of three choices, and this will depend on the problem. So it'll either be that the population mean is less than that value, population mean is greater than that value, or simply that it's not equal to that value. Okay, and then we're going to observe a random sample of the population, and this is kind of just what we said. We have x1, x2, all the way up to xn that are IID normal with mean mu and variance sigma squared, where we know what sigma squared is. Okay. So that's kind of your setup to think about what setting am I in here. Fourth step in our little list of steps here to do these tests, again, is we want to perform the test procedures. And so this is something we sort of talked about. I think on Wednesday we talked about this. But our test statistic here is going to be something called a z, which is exactly what you would expect it to be. You're going to take the x bar, you're going to subtract off the hypothesized mean, and you're going to divide by the standard deviation, which is now sigma over the square root of n. And again, we get here because x bar we know is distributed as a normal random variable here with mean mu and variance sigma squared over n, so that leads us to that. And when the null hypothesis is true, then the distribution of x bar. So again, the null hypothesis says that the mean is actually equal to mu 0. So when that's true, our test statistic is going to have a normal distribution, a standard normal distribution. And then from your data, you're going to be given, you have this random sample of numbers. You can calculate the sample average, which is x bar, which will allow you to calculate the observed value of your test statistic down here. So you observe information, calculate the average, and then you plug that in right there. And otherwise, we know how to calculate the test statistic, right? The mu 0 comes from the null hypothesis, and sigma, we're assuming that we know what sigma is. Okay, so that's our test statistic. Again, then our next step is to make a conclusion. So we're rejecting the null hypothesis, or we're going to fail to reject the null hypothesis. Let's say reject versus fail to reject. And we do that based on the p-value. So again, we talked about what the p-value is, and we calculate it slightly differently depending on what our alternative hypothesis is here. So for this first alternative hypothesis, our p-value is going to be equal to the probability that a standard normal random variable is less than the lowercase z here. This is our calculated test statistic, which was x bar minus mu 0 over sigma over square root of n. Okay, for the second one here, our p-value similar, but probably that a standard normal is bigger than our test statistic. And finally, for the last case, our p-value. Again, remember when we're looking at a not equal to alternative, that's a two-sided test, and so we want to consider extreme values in both tails of this distribution. So this is going to be 2 times the probability that our standard normal is bigger than the absolute value of our test statistic. And the nice way to keep this straight is to note that we have the same inequality signs in our alternative hypothesis and in your calculation of the p-value. So if your null is that if your alternative is that the mean is less than this value, then you want to calculate the probability of being less than that value, and vice versa. That's a way to keep that straight. Okay, so that's our p-value, and then to actually make our conclusion, we need to, for a particular alpha level, so for a significance level alpha, that will be given in the problem. So if our p-value is less than alpha, what are we going to do? Anybody remember? So again, we're trying to decide if we want to reject the null hypothesis or fail to reject the null hypothesis. And the p-value tells us the probability. The definition was it's the probability of observing a test statistic that's at least as extreme as ours was if the null hypothesis was true. So if the p-value is small, if the p-value is less than alpha, what do we want to do? We want to reject the null hypothesis, exactly. So the idea being that p-value sort of gives you an idea of sort of how likely it is that you observed what you did if the null hypothesis is true. So if the p-value is small, that means that probability was small, and so you want to reject the null hypothesis. And our conclusion is that conclude that there is evidence in favor of the alternative. The parallel here would be sort of like in our legal system example. It would be that if we reject the null, that's like saying the defendant is guilty, right? We've collected evidence to say that they are guilty there. Okay, so if our p-value is bigger than alpha, we do the opposite thing. We will fail to reject the null hypothesis. Again, and our conclusion here is that that there is not enough. There's not enough evidence to support the alternative. So if we fail to reject the null hypothesis, that's we're saying that there's not enough evidence to sort of support our alternative claim. We have to sort of stick with what our initial claim in the null hypothesis was. Again, that would kind of be like the jury determining that the defendant is not guilty, right? They're not saying that they're innocent. They're just saying we haven't seen enough evidence to show us that they are guilty. Okay, and then just our favorite line down here. We always want to make sure to give a good conclusion, and to do so, we want to make sure to do that in the context of the problem. So we'll do an example of that in just a moment here. Okay, so making a quick connection back to confidence intervals, and sort of again, we've already sort of talked about how they're doing sort of the same thing, but for our confidence interval, we found these critical values, maybe z sub alpha over 2 or something like that. Again, these values again are just such that probably that a standard normal random variable being bigger than z over alpha equals alpha. So it's just that value such that the probability being larger than that is alpha. Again, you can kind of think about if the p-value is less than alpha, or that will happen if and only if your your test statistic is larger than the critical value there, so larger than whatever z sub alpha over 2, and similar. So this was the idea that for a confidence interval, you could sort of think about the idea you'd reject the null hypothesis if mu 0 is not in the confidence interval. So you calculate a confidence interval and you find that your hypothesized value mu 0 is not in that confidence interval. That will lead you to reject the null hypothesis at the same significance level as you've constructed your confidence interval under. So just keeping in mind this duality here sort of between intervals and tests. Any questions you guys can think of? Comments? No? Okay. Let's do an example here then. Let's see how this thing works. So So one of the reasons that I made the extra credit assignment as it is that hopefully next week or after that we can throw some more interesting examples in here. So for now, bear with me. We can go with the sort of the book examples, which might not be as exciting. Hopefully we'll have some better examples to talk about here. Anyway, so here in our example, we're looking at the melting point of a certain brand of vegetable oil, and we take a sample of 16. We take 16 samples and find the melting point for each one of these oils. And we find that our sample mean there, x bar, is 94.32. Okay, and we want to sort of, here our assumption here is going to be that the distribution of these melting points is normal with known variance or known standard deviation. Same thing. Okay. So the question that we want to know, or what we're told to do here, is we want to test these hypotheses. So we're just, instead of being told in the context of the problem, we're just told what the hypotheses are. So we want to test the null hypothesis that mu is equal to 95 versus the alternative, which says that the mean is less than 95, and we want to use a significance level of 0.01. Okay. So hypotheses are already set up for us, but let's kind of go through our strategy here. So we're interested in here mu is the true average melting point for this brand of oil. Okay, and so we have a normal distribution. That's good. We can use this. We have a normal distribution, but we need to check one other condition. We always want to make sure that we have a random sample, right? That's kind of the theory that we need here. So are we told anything about the nature of our sample here? Doesn't say. So it's not stated that it's a random sample. So if we want to proceed here, we have to assume that it is. So we're going to make the assumption that we have a random sample here. Again, maybe you're getting tired of hearing me rail on this, but again, sort of the point is that random sampling is sort of an unbiased way of sampling from your population, and if we have a random sample, then it's sort of we've done all we can to make sure that our results are not going to be biased in some way. So, for example, go back to my favorite example, if I'm looking at the height of students at Ohio State, and I sample 10 male students and then do a confidence interval for the average height of students at Ohio State. That's not going to be correct, right? So there I don't have a random sample. I've taken all subjects from one gender, and that'll give me a result that's probably not going to be very meaningful. So again, the point is here we just keeping in mind that in order for these methods to work and give us something that's meaningful, we want to make sure we have a good sample from our population, and sort of our easy out is to say we have a random sample. We sort of need that to be the case. Okay, so since we have a normal distribution, so we have our random sample is from a normal distribution where sigma squared is known. So we can use the z-test here, which is what we're talking about. Okay. So again, once you know what parameter you're looking at, once you have your hypotheses set up, once you've observed a random sample, you're ready to actually do the test. So our test statistic here, again, remember, is z, which is x bar minus mu 0 divided by sigma over the square root of n. Remember, our null hypothesis was that mu is equal to 95. So that's our mu 0. That's our hypothesized value. X bar we observed was 94.32. Subtract off the hypothesized mean there, 95. Our standard deviation is 1.20, and our sample size was 16. Calculate that out, that'll give you negative 2.27. Okay, so again we have here's our normal distribution that tells us about our test statistic z. It's centered at 0, and the value that we've calculated is down here at negative 2.27. Okay, so I have my test statistic. I'm now ready to calculate my p-value, and this is the probability that z. And then what probability am I interested in calculating here? So I have a negative 2.27 here. What probability do I want to calculate here? I think I heard it. Less than, exactly right. So again, my alternative hypothesis was that the mean is less than 95. And so that's why I'm using a less than here. So I want to calculate this probability here. And again, now just standard normal, going back to the table. I'm not going to go over that step again. You can find this probability is equal to 0.0116. This is from the table. All right, so we've calculated our test statistic, we've found our p-value, and now we're ready to make a conclusion. Okay, so our p-value is 0.0116, and our significance level here, alpha, is 0.01. Okay, so how does our p-value compare to alpha? P-value is bigger, exactly right. So therefore, what is our conclusion? P-value is bigger than alpha, we're going to do what? Fail to reject, absolutely. So we're going to fail to reject the null hypothesis. Again, doesn't matter how much bigger than alpha our p-value is there, but it's just the fact that it's bigger than alpha, we're going to reject fail to reject the null hypothesis. So let's say exactly what that means here. So, and here's sort of your template way of interpreting these things as well. So what we'll say is that since the p-value is bigger than 0.01, which is our alpha, we fail to reject the null hypothesis. And what that means is that there is not enough evidence to conclude that the alternative hypothesis is true. So what that said was to conclude that the mean melting point, the true average melting point, is less than 95 degrees. Okay, so we failed to reject the null hypothesis, and what that means here, I failed to reject the null hypothesis, so I'm sort of going with the null. So I don't have enough evidence to conclude that the true average melting point is less than 95 degrees. Is that okay with everybody? No questions? Okay. So one more part to this question before we move on to case 2 here. And this is kind of going back to thinking about the different errors that we can make. So we've used a level of significance of alpha, and we want to know something about the type 2 error when the mean is actually equal to something else. So remember, beta equals the probability of a type 2 error, which was the probability that we fail to reject the null hypothesis when, in fact, the null hypothesis is false. Okay, and more specifically here in this problem, what we're saying is that if the mean, so we're saying that the mean is actually equal to, if the mean is actually equal to 94, what's this probability? So if the mean really is equal to 94, then the null hypothesis was false, right? We said it was equal to 95. If the mean is actually equal to 94, then we have made an error here. We've made the wrong conclusion. Okay? Okay, so how do we do this? So again, since the alternative hypothesis said that mu was less than 95, that means we have a one-tailed test. In which case we will reject if our test statistic is less than or equal to z sub alpha. So if it's less than or equal to that critical value, then we will reject the null hypothesis. Okay, so here because alpha equals 0.01, we will reject when the test statistic is less than or equal to, sorry, I've made a typo here. I wanted to have a negative sign in there on that previous line. So I want to reject when my test statistic is less than negative z.01, which is negative 2.33. Okay, so if we reject when that's the case, then we will fail to reject when the test statistic is bigger than negative 2.33. Okay. Okay, so what that means here, so we will fail to reject when our test statistic is bigger than negative 2.33. Well, our test statistic, remember, is x bar minus mu 0 divided by sigma over the square root of n. Again, if the mean is really 94, this is x bar minus 94 divided by our standard deviation 1.20 over the square root of 16. So we'll reject when this thing is bigger than negative 2.33. Okay, so again, we can solve through for this, and that means we'll reject if and only if the x bar is bigger than negative 2.33 times 1.20 over the square root of 16. I'm sorry, I made another mistake here. My null hypothesis was 95. So we'll reject when our test statistic is bigger than negative 2.33, which means that we'll reject if our sample mean is bigger than that, which is 94.301. Okay? So our probability of a type 2 error here, when the true mean is actually 94, is the probability that we fail to reject given that the null is that the mean is equal to 94. The true mean is actually equal to 94, which what we just worked out, that's the probability that our sample mean x bar is bigger than 94.301. Okay, well, x bar still has that normal distribution, so this is the same as the probability that z is bigger than x bar, which is 94.301 minus the mean, which is 90. We're saying is 94. The true mean is 94 divided by 1.20 over square root of 16. And I'm putting 94 in there because I'm conditioning, or I'm assuming that the mean is actually equal to 94. So my standard normal is normal, but it has mean 94 here in this probability. Okay, this is the probability that a z is bigger than 1, which is equal to 0.1587. Okay, so what does all this mean here? Again, remember the type 2 error is, oh yeah.
So when you pick 94, could you pick like any value less than 94?
Yeah, so the issue is, so the definition of our type 2 error is we're figuring out the probability that we failed to reject the null hypothesis, given that the null hypothesis is false. So that will depend. So to actually calculate this, you have to pick a value of the mean, and it could have been anything, right? hold that thought. Let's come back to that in just a second. So if what this number tells us is that if the mean is actually 94, so we don't know what the mean is, but if it's actually equal to 94, then the probability that we've made the wrong decision here is 0.1587. So let's write that down. So if the true melting point is actually 94, then we have mistakenly failed to reject about 16% of the time. Okay, so that's probably that we've made the wrong decision. If the true mean is actually equal to 94. Yeah, Kyle.
So in this situation, like, would that probability of, I guess, the type 2 error be related to the like area between the two values? Like, that looks about right between 94 and I guess 95. If that was the real mean.
Yeah, good question. So the I think actually let's go ahead and draw this picture. This might help a little bit. So here is the distribution of my test statistic here. Well, actually, this is the distribution of X bar, not my test statistic. Okay, so what this says is that if the null hypothesis is true, that thing's going to be centered at 95, right? So the curve will look something like that. And the X bar that we actually observed was down here at at 94.32, and so we found our p-value was there. Okay, and so we're gonna, well, sorry, what we found is that that big calculation we did down there, or just before, was to find this value, which was 94.3. And so that if our test statistic was anywhere down in this direction, we were going to reject. Okay? So then now we're saying, what if in the other case, so let's say if the mean is actually equal to 94, then our distribution, wow, that's not good. Then our distribution looks something like that, right? It's normal, still a normal distribution, but it's shifted over to be centered at 94 instead of 95. And so what we just calculated was this whole area there. So the shaded in red area was that represents, or anything to the left of that represents that's 0.01. So this area here is 0.01, and then what we just found was that this area here is 0.1586. Is that right? 1587. So it's if the mean was really shifted over to 94, then the probability that we fail to reject is going to be it's going to be that other side there. Does that answer your question, or were you thinking more? Sorry, does that answer your question?
Well, not necessarily. Like, no, I was asking, I guess not related to the 94.37, but like on the red curve, the probability between 94 and 95, would that be around 16%?
Oh, so you mean?
With like standard deviation of 1.2. Would that be related to the...
It might be close. You're right, but that would be completely by coincidence if that was the case. Yeah, yeah. So then back to your previous question. So again, the probability that we just calculated depends on what we picked our alternative value to be, right? So that the probability of a type 2 error depends on what the alternative, what the mean actually is. So if you picked your mean if you wanted to find the probability of rejecting, given that the mean was actually down here at like 90, I don't know, 90 or something like that, then that probability is going to be even bigger, because it's you're still calculating the area that's below here. So as your mean gets further away from what you've hypothesized it to be, you're going to have more and more of a chance of rejecting the null hypothesis.
So in general, we pick the closest like integer to the value?
Yeah. So in general, if I ask you to calculate a type 2 error, I'll say calculate the probability of a type 2 error if the mean is actually equal to this. So it's kind of like if the mean was off by if we're off by 1 unit there, I mean it's just the number that I threw in for this example. Yeah. Yeah. Okay. All right, so let's move on to our second case here, and again start moving a little more quickly here. Again, same setup as we were before. We just don't know what the population variance is. So we're still interested in looking at mu, which is the population mean. Our hypotheses are going to be, we're going to say as before. The hypotheses are not going to change here in this case. And we're still going to observe a random sample. We have x1, x2, IID normal, mean mu, variance sigma squared. But now this is an unknown variance. So getting slightly more realistic here. Okay, so again, our test statistic changes, but it should change exactly like you would expect it to. So before we had before our z was equal to x bar minus mu 0 over sigma over the square root of n, and now we're just plugging in the sample standard deviation here. Kind of just like we did for confidence intervals. And now this thing has a t distribution, as we discussed before, and so we can use that distribution to calculate our p-value like we did in the previous example. So for when we observe data, we can actually calculate our test statistic, which is down here at the bottom. Okay, so same deal for the p-value. I'm going to calculate this in exactly the same way. My p-value for this first alternative hypothesis is going to be equal to the probability that a t random variable is going to be less than my observed test statistic. Similarly, if I want an alternative of being greater than, I'm going to find the probability of being greater than that value. And if I have a two-sided alternative hypothesis, I'm going to find the probability of being bigger than the absolute value of my test statistic. So I'm going to look at both tails of the distribution there. And again, we can find our p-values. We're going to use a table again. You could use table A5, which I think is the table that you guys used for finding critical values. We're actually going to use, well, the book nicely provides us with a second table that makes this a little bit easier to find what these p-values are. Okay, and the conclusions are going to be sort of as before. So when the p-value is less than alpha, we're going to reject the null hypothesis, and when it's bigger than alpha, we will fail to reject. Okay, so this sort of the only change here is in the calculation of your test statistic and how you find a p-value. You're going to be using a t instead of a z. Okay. And I guess similar to before, again, if you're thinking about this in terms of critical values, you could compare your test statistic to a critical value, just like you could calculate a p-value. It's going to be the same strategy here. Okay, quick example here. Here now we're looking at a random sample of 26 observations on the escape time for oil workers in a simulated exercise. And so from this data we have a sample mean and sample standard deviation of 370.69 and 24.36. So I don't know what this game was, but this is the data that we have here. So this is my sample mean x bar, and this is my standard deviation s. Okay, so suppose that the investigators had believed that sort of the average, the true escape time would be sort of at most 6 minutes. So we want to know, do the data here contradict this prior belief? And then we're told an assumption to make about the distribution of these escape times. Okay, so again here we want to, our parameter of interest here again is still mu. What that is here is this is the true average, escape time for this game. Okay, now I want to set up my hypotheses, the null hypothesis and the alternative hypothesis. And again, both of these are looking at mean, the mean mu. And the null hypothesis always has an equal sign in it. Okay, so then to actually set up these hypotheses, I have to sort of think about what is the question of interest here. So again, the investigator's sort of proposition or prior belief here is that the true mean here would be at most 6 minutes. And so remember, the claim that I'm interested in testing is what I'm going to put in my alternative hypothesis. So what should my alternative, how can I complete my alternative hypothesis here? I want to see if this true, or the claim anyway, is that this true mean is at most 6 minutes. So it's either less than or greater than, right? Less than 6, yeah. So I want to see if the true mean is at most 6 minutes. Well, let's say 360 seconds. Okay, and then you can just put the same number 360 in your null hypothesis. Okay. Actually I feel like in these problems, this one maybe is not too crazy, but I think the hardest part can often be setting up your hypothesis. So is everybody okay on? My claim is I'm saying that the average escape time is at most 6 minutes, 360 seconds, and I want to see if that's not true. Yeah.
Wouldn't we actually want the opposite alternative hypothesis, because the null hypothesis should be essentially that mu is less than or equal to 360, because that's what they expect. So if we reject it, we're actually going to confirm our null hypothesis too.
Yeah, so the response was that shouldn't our alternative hypothesis be the other way around? So if I'm sort of my prior belief here is that the mean is actually is at most 6. Now I want to see if my data contradict this prior belief. So yes, I think you are right. I had that in my notes and it didn't make sense to me, but I think you are in fact correct. Yeah. So sorry about that. So I wrote the wrong thing here. Let's just note that this should be actually a greater than. My null hypothesis, again, sort of my prior belief is that it takes them at most 6 minutes. So if it takes them less than 6 minutes or less than 360 seconds, I I guess that's good in some sense, right? I want to see if the data that I've found sort of contradict that claim. So I want to see if it actually takes them longer than 6 minutes to escape. That's excellent. Thank you for catching me on that. So the key here is that do the data contradict this prior belief? So I'm interested in seeing if my data contradict my prior belief. That's why they're set up this way. Sorry for the writing the wrong thing up there. Everybody okay with that? Okay. So those are our hypotheses. Our next thing is to sort of make sure that we're able to use the procedure that we have here. So again, we have a normal population and a random sample. It's stated in the problem. So we can go ahead and use this test statistic that we have up here, or that we looked at on the previous few slides. Okay, so here our test statistic is going to be t, which is again x bar minus mu 0, same thing, just now we're dividing by the sample standard deviation over the square root of n. Here our sample mean was 370.69 minus our hypothesized mean was 360, dividing by the standard deviation 24.36 over the square root of 26, which is 2.24. Our degrees of freedom here, n minus 1, is 25. Okay, so then I have my test statistic. I can now use this to calculate my p-value. So my p-value here was the probability that a t random variable. What probability am I interested in finding here? So 2.24 goes in here. What's my inequality in there? Greater than. And that's again because my alternative said that the mean was greater than 360. Okay, so now's where we need to look at table A.8, which I think is in your notes there. And table A.8 is a little different than the previous T table we looked at. It's more like the sort of the standard normal table that we saw before. So the degrees of freedom are listed in the top row there. And then the actual values of your test statistics, sort of like the Z table, are listed in that leftmost column there. So if you go down to the, and then the table gives you area above that value. So this is the area that we want. If you go down to the 2.2 row and you scan over to the 25 degrees of freedom column, it's on the second page there. That will give you p-value of approximately 0.019. So this is approximately 0.019. This is from table A.8. Bear with me real quick. I'll finish up here just in a second. Okay, and just to finish this thing off, so our p-value here is 0.019. The alpha that we were told to use in this problem was 0.05. That was stated there. So our p-value is less than alpha. So therefore, what is our decision? Do we reject or fail to reject? We reject. And let's just quickly write down what that means. So because the p-value is less than 0.05, we reject the null hypothesis. What that means is that there is sufficient evidence to conclude that the true mean escape time is more than 6 minutes. Okay, so we rejected the null hypothesis, and here that means that we do have sufficient evidence to conclude that the time it takes them to escape in this drill is more than 6 minutes. So we do have evidence to contradict their prior belief. Okay, guys, sorry for keeping you over a minute here. Thanks for being here. Have a great weekend. No class on Monday. Hey, Kyle. Yeah.
Okay, so to know when to use like Z or T, I know there's one on the homework, but I eventually figured it out because it was like sample standard deviation.
Yeah.